Hello everyone, we are batch A17. Our project title is about a design of low profile microstrip patch antenna with defected ground structure for wireless applications. Coming to the contents of the project, in our project we are having abstract, objectives, introduction, literature survey, designing methodology, antenna modeling, results and discussions, conclusion and references.
Coming to abstract, we proposed a dual band microstrip patch antenna with a defected ground structure for 5.3 GHz and 7.0 GHz applications. A Google Lens logo shape is created here. The dimensions of the antenna is 20 by 20 mm. Here we use a FR4 substrate and the dielectric constant is 4.4. The return loss characteristics of dual bands are minus 20.56 dB at 5.3 GHz and minus 19.7 at 7.4 GHz. For both applications, the VSWR is less than 2. The total gain of the antenna is 4 dB.
Our main objective is to design a low-profile microstrip patch antenna for wireless applications using ANSYS HFS software. To enhance the performance of the antenna using DGS technique. To improve the characteristics of the antenna such as return loss, radiation patterns, directivity, and gain.
Coming to introduction, microstrip patch antennas are popularly used because of their ease of fabrication, affordable cost, and conformal structures, and etc. And they have the advantages over the conventional antennas such as horn antennas and dish antennas. And these microstrip patch antennas consist of a ground plane and patch. In between, there is dielectric material in between them. So, and these are used for short range applications and high frequency applications above 100 megahertz. And also, these patch antennas suffer from the drawbacks of limited bandwidth, poor gain, and low directivity, so which constrains its applications. And defective ground structure is a novel approach which is used to improve the performance of the antenna. It is purposefully created a defect on ground plane. It is usually a H-out pattern on ground. Next. So, coming to literature survey, so we presented literature survey of 6 papers. Here, there is various techniques to improve the performance of the antenna, such as taking different shapes and using parasitic elements and antenna arrays. So, like that, so we selected DGS technique to improve the performance of our antenna. Coming to design methodology, so first step is to select the design parameters. Means we need to select the operating frequency of the or working application or operating frequency for which we need to design the antenna. And second one is choice of appropriate substrate material. So we need to select the material. There are different materials available in the market, so we need to select which should fit our applications. And next, transmission line modeling. It is nothing but feeding techniques. What type of feeding technique we need to use? There are feeding techniques like coaxial feeding, line feeding, aperture coupling. So like that, so we use it line feeding in this. After that, we need to simulate the antenna. If you get desired frequency or operating frequency and acceptable gain and return losses, then we can go for testing of the antenna and verification. Else, we need to make correction to our antenna, such as changing the structure of patch or putting slots in it, or altering the position of the feed, or using DGS techniques.
Coming to the software description, we are using HFSS software, where HFSS is a multi-purpose full-wave 3D electromagnetic simulation software, which is used for designing and simulating the high-frequency electronic products. Where HFSS is a high-frequency structure simulator. It is used several commercial tools, which is used for antenna designing. Dimensional view of our antenna. Here we can see both the antennas, antenna 1 and 2, where we have substrate, port, ground, and patch, which are represented in the slide. So coming to the antenna modeling, here we can see the parameters and dimensions mentioned for the antenna. And the results and dimensions which are included are return loss, VSWR, gain, surface current distribution, field intensities, and radiation patterns.
Return loss for the antenna 1 is minus 24 dB at 6.1 gigahertz frequency. And VSWR, the VSWR value for the antenna 1 is 1.1 at 6.1 gigahertz frequency. Gain is the three-dimensional view of radiation field. Red indicates high gain, and for the antenna 1 gain is 4 dB.
So here we shown the current distribution of the antenna one for 6.1 gigahertz. Here shown electric and magnetic field intensities of antenna one for 6.1 gigahertz. So radiation, coming to radiation pattern, the blue line indicates the copolarization and red line indicates the cross polarization of antenna one.
Here we can see the modeling of an antenna 2, which is a Google lens shape. So here we are representing patch and ground, where patch is the front view of the antenna 2 and ground represents the bottom view of the antenna. So these are the dimensions of the antenna 2 of Google lens shape. So we can see here parameters and dimensions which are measured.
So coming to the results of second antenna. So return loss value for antenna 2 are minus 20 dB at 5.3 gigahertz and minus 19 dB at 7.4 gigahertz. Coming to our voltage standing wave ratio. So we got minus 1.2 at 5.3 gigahertz and 1.24 value at 7.4 gigahertz. And gain of our proposed antenna, second antenna is also same as the first one. It is 4 dB. And here we shown the surface current distributions of our antenna at two frequencies, at 5.3 gigahertz and at 7.4 gigahertz. So, and here we have shown electric field intensities and magnetic field intensities of our antenna at both the frequencies 5.3 and 7.4. It's coming to the radiation pattern. Here we have shown the radiation patterns of our antenna. So we can see a good antenna decides low cross correlation value. So here we can see that the cross correlation is indicated using red color line. So it is very low compared to the copolarization, which is this side. So these are fabricated antenna. So as you can see the patch. So it is 20 by 20 mm, as we already said. So it is 2 centimeters. So these are the measured results. So we got the results very similar to the simulated one. So coming to the conclusion, so finally the proposed antenna is working for two frequencies. It is 5.3 and 7.4 gigahertz, in which we use TGS technique to improve the performance of antenna, and also it should some slots on the patch itself. And next, coming to the voltage standing wave ratio, we obtain less than VSWR less than 2 at both the frequencies, and gain of the antenna is 4 dB and directivity is 5.58 dB, and the radiation efficiency of our proposed antenna is 67%. So these are the references. Thank you.
Thank you.